welcome to episode 128 of ArrayCast. I hope I got that number right because I realized just as we went live that I didn't actually have it in front of me, but I think I did. And we have a very exciting episode today. We've got three guests with us who I guess I should mention them now. Well, actually, I'll mention them in a sec. But if you're watching this on YouTube, which I think is, I don't know what percentage of our listenership, but it's the minority, you can already see all three of their names. The audio listener, though, will have to wait a few more seconds. And I guess with that, I'll do a brief introduction. Adam can go first, then I can go. And actually, should we just change it so that we can all go around? Because I just realized that we're bringing back Steven. Spoiler for the audio listener. Steven Taylor, longtime panelist, has come back for this special episode. And so I was just thinking that I guess he should do the brief introduction. So maybe what we'll do is we'll go around and we'll do brief introductions from everyone, and we'll go from there. So we'll start with Adam, and we'll finish with me, and then we'll go Steven, Alex, and Jacob will do last for our guests. So kick us off, Adam.
Yeah, I'm Adam 𝗔𝗿𝗆𝗪. I am head of language design and longtime APLer at Dialog Limited.
I'm Steven Taylor, an APL and Q enthusiast and one-time KX librarian.
Hi, I'm Alexander 𝗦𝗛𝗢𝗪. I'm a Q enthusiast and the founder and blogger behind DefconQ.
Yep, and I'm Jacob Loveless. I'm a very long-time K and Q developer.
Awesome. And as mentioned before, or actually I'm not even sure if I mentioned it before, my name's Connor, host of ArrayCast, fan of all the array languages. I'm very excited to hear about the topic for today. But before we get to that, I'm going to hand it over to Adam, who I believe has 3 announcements, if I recall correctly.
Or we could call it 4, maybe. Right. So first, a couple of deadlines. On July 31st is the deadline for early bird 10% off special for the Dialog user meeting. You get that rebate because the schedule for what happens at the user meeting isn't quite settled yet. Only the workshops are settled. So if you're willing to sign up, even though you don't know exactly what the presentations will be, you get some money off. And also there's the APL challenge, this introductory course/competition where you can win some money for learning a little bit of APL and using it. It has a round finishing the same day, July 31st. Then a couple of weeks ago, we had a workshop internally at Dialog, and it was on using LLMs with APL. And so we're trying to educate our employees on how to use LLMs effectively and safely. And there's an interesting blog post that we'll put a link to as well on using APL with LLMs and how to make them do that, be able to write some sensible APL. But out of that came also an old project, something I started 3.5 years ago when I was on parental leave and I was holding a baby with one hand and then I was typing a little bit of JavaScript with the other hand. And I made the bare bones framework for a game that, like a top-down dungeon crawler game that would teach you some APL, but I never had a chance to finish it because the baby grew up. And then I figured, well, as an experiment for this, a material for this workshop, I would throw the LLM at it and see if it could finish up the game. And I think it turned out really well. We'll leave a link to that as well.
Awesome. So links for all 4 of those things will be both in the YouTube description and the podcast show notes after I update this later. And with those out of the way, we're going to do something a little bit different today. So because we have our former panelist with us, he knows much more about the K space, and we're going to throw it over to Steven. And Steven's going to lay the groundwork for what we're going to be talking about today. And so with that, we'll throw it over to you, Steven.
Well, thank you, Connor, and let's start by frankly admitting that Alex and I screwed up.
Uh-oh.
He and I are both romantics about the Q and K languages, and when the KX module manager appeared, we announced a meeting at Milden Hall in Suffolk for this September, so that people could get together and plan and start building open source Q packages. Yeah, that was a romantic vision. It was a wonderful idea. However, KDB developers turn out to be actually rationalists. And they saw what was actually quite obvious and what we didn't really want to admit, which is that the price of KDB licenses restricts the language usage to some very deep corporate silos. And those corporate silos had no use for community code resources. And so we got very few registrations and wound up canceling the meeting. And then something very significant happened. And our guest today, Jake, did it just, I think, the week before last. And it changes the landscape. And now there's still some kind of a meeting happening in Suffolk in September. It's emerging what it is in real time, but it's starting to look like ground zero for a QK open source community. We're pretty excited about it. I'm not going to spoil what we're going to learn from Jake, but that's about it. Something really exciting is happening.
All right, so with that, I guess we'll throw it over to Jake, and you can tell us about everything you've been working on and what you released just in the last little bit.
Oh, sure. So like I said, my name is Jacob Loveless. I've been a K programmer since probably very early 2000s, maybe 2001 at a company called Appian. And then I did that, worked for DoD, then I went to Wall Street, was at Wall Street for a very long time. And then I left a little more than 10 years ago. And I was on garden leave, which I think is a very garden leave is fantastic.
It is fantastic. I've never been on it, but when I hear people are on it, I was like, the first time I heard about it, I was like, what? You're getting paid to do?
No, you're getting paid not to work anywhere else. You're actually getting paid to work in your garden, is what they call it. And while I was on garden leave, I started a project to basically go rebuild the kind of a K4 and a Q interpreter, and I called that L. And so and there had been kind of different versions of that all along the way, but about maybe a month ago, I got to the point where I was like, hey, let's actually post this out to the community, see if anybody else wants to play with it. So L is a K4 compatible, Q compatible. Its goal is to be a drop-in replacement so that you can take kind of KDB style workloads and run it, anywhere, right? You don't need all of the kind of, as Stephen said, can we kind of take this language and bring it to a larger community in a runtime that anybody can run. And so it was a really small group of people on basically a Discord server, and then we put up a website, and then it got pretty big pretty quickly. So I think we had, in the first 2 days, the website got discovered. It's 48,000 people came to the website. We had over 300 downloads of the binary, so which is a good thing. The binary is small because bandwidth is small. So that's the thing that has kind of come out here, I'd say, in the last 30 days has been people downloading the L interpreter, running K4 and Q code. And for me, it's really exciting to see not just, everybody that kind of I know in this community, but brand new people coming from completely different backgrounds. Like I had somebody last week who emailed to the list group, and they were working on telemetry data for effectively cars. I had somebody who emailed that was working on like biogenomics and saying, hey, can I use this for this? And I was like, yes, it'll be great for that. Let's talk about, how do you restructure these kind of problems in an array oriented thing. And by the way, it turns out that K and Q just absolutely crush for that kind of workload. And we built a RAG, which is one of these AI vector search things. It was like 20 lines, and really, really, really fast. So yeah, so that's what it is, and it's got a public website. It's at lv1.sh because you needed a short domain, and that's as short as I could get it. So yeah, that's the big out there in the open.
Yeah, so it's very exciting. I think I saw it first on the APL JK Reddit. It was posted there by someone, and very exciting. But I guess there's a number of things we could talk about first, but probably notable is the differences, like the runtime differences. So do you want to talk about what L offers that the previous interpreters, like, because they're not exactly like, it's a drop-in replacement from like a, what do you call it, language level point of view, but from a runtime point of view, there are some differences, which I'm sure listeners of this podcast who are programmers, some are maybe not programmers and just curious, but I'm sure a lot of the listeners would be curious to hear those differences.
Yeah, it needed to be language compatible because, frankly, I have 20 years of code I didn't want to rewrite. That said, I did want to go experiment with, kind of new ideas under the cover. And I think the big ones are, well, the first one, which is pretty straightforward, is just SIMD, right? You want to actually get every cycle out of the chip that you can. So take all of your primitives, sit very quietly and make sure that you can implement SIMD versions of that. Then once you have that, I wanted auto threading. So K4 had a concept of peach, of parallel each, which is wonderful. But, it kind of changes the code. So I wanted something like, like a reduction, like sum or something like that, to actually automatically thread over the array and, kind of do that map reduce concept, but do it completely transparently.
Does K not have any guarantees of stability of results like that? Or
with regards to floating point?
Of what? Yeah, floating point, yes.
Yeah. I don't really know what KDB has. L's floating point is, there's effectively a comparison tolerance that comes out. And
right.
Yeah, if you sum them in different directions, obviously you would get different values. So the reductions are taken in chunks, but the comparison tolerance is I think it's 1e to the -17. So it's, as you get far enough out there, you can get different answers, but kind of the interpreter itself hides that comparison tolerance at a certain level. Did that answer your question? So you get the same answer every time, but because you are parallelizing and reducing reducers, right? You can, if you would get something different than if you were serially just walking.
And
you would get
that's why I'm asking.
Yeah, just like if you would get something different if you reversed it and walked through it.
Yeah, I know. I'm asking because we have this problem with dialog. Our summation code and interpreter was written pre-SIMD, and now we can't change it because our customers want stability. You don't want the amount of money in people's bank accounts to change because we changed the summation algorithm. And you might ask, why are people using floats for money? They are. What can I do?
I think, well, if you use floats for money, you should really think very carefully about where your life went wrong. But that is actually kind of a good segue to the last thing. So the last thing was this idea of, I call it compression because I can't think of another more elegant way to explain it. But can you take quantizations, maybe another way to say it, but basically, can you take this array and can you store it in a different format that allows you to work on smaller memory footprints? So can you change underneath the covers? Can you compress that array into another format? And then most importantly, can you work on that compressed array? Can you make all of the array operators, can you make all of the verbs and adverbs work on what I call compute uncompressed, or lots of people call it compute uncompressed? And when you do that, you could do something like, if you are storing money as floats, like behind the covers, L doesn't store that as a float. L actually goes ahead and promotes that into an int, and then kind of does this very clever little trick underneath the covers to allow you to operate in the int space, and then gives it back to you in the floating point space, or the real space, depending. So so those three things, kind of the SIMD, the auto parallelization, which is different than SIMD, and the compression, those are probably the three giant pillars that are really fundamentally different. I mean, compression, I started doing compression a couple of years ago, and it was enough of a performance improvement that I actually had to delete everything and start over, because you basically change the entire representation of the object. But it turns out that that is the unlock from a performance standpoint. You can really only make these things go so fast in SIMD. You can only make them go so fast, you know, across multiple cores. I mean, bandwidth, memory bandwidth is the enemy. So, you know, I say this all the time, but making things go faster is actually pretty simple. You just move less data over a shorter distance using a more efficient protocol. So if you can take that array and move it into a smaller type, you can move less data. You know, you have to be very cognizant of making sure that where that array is relative to the core that it's going to operate on, that's your shorter distance. And, you know, really the protocol you can think about as the actual operation, the SIMD operation underneath the covers. So those are kind of the three crazy ideas.
But that doesn't sound very crazy. I misunderstood when I was reading up on this. I thought by compression you actually like compress data as in zipping it, but it's not. You're just talking about using data types.
Yeah, dictionary compression isn't really. I don't think really helpful, because you can't really operate on it. You can't really operate on it. I think.
Well,
yeah.
you could, like, let's say you had a matrix stored as some vectors, and it was fairly sparse, and you actually compressed each row separately, and then you want to reverse the order of the matrix. This you can do without decompressing the components, right?
Yeah.
So that was the idea I got when I heard about like compression. It's like, well, how in the world do you write algorithms to operate on the compressed data? But if you just mean data types that are more dense for the data that's actually there, then that's pretty regular fare for array languages. I thought that every serious array language already did this, and if obviously you can't tell me about the source code at of official KDB. I assumed that was happening underneath the cover there as well.
Well, I think let's take a simple example. Probably the easiest codec that there is to you can kind of almost see it in your mind is the frame of reference, right? So imagine you've got, you know, I don't know, 255 plus till 1,000, all right, or 255 plus iota 1,000.
Yeah.
So now you've got this big array of 32-bit integers. Frame of reference basically says find the minimum, right? Store that offset as the base, remove that from everything else. And then the question is, now you've got a base, and then you've got a payload, right? You remove the base from the array, and now you've got a payload. Is there a bit width that can represent that payload is smaller than the original bit width? And it turns out that the answer is yes. That happens like all the time, right? You can you might have an array of 32-bit integers that you can represent as, as a short. Or, if you kind of take frame of reference and apply delta on top of it, you might actually be able to get that down to 4 bits, right? So, and, it's really nice about frame of reference, aside from the fact that it's kind of easy to see in your mind, is if you make everything do that from the beginning, then you kind of get these free little performance wins just by the structure of that. So to give you an example, let's say you wanted to add an atom to that array, right? Well, obviously there's no reason to do that element wise. If you're going to add the atom to every single value of the array, you would just add it to the base. So these kind of operations become faster. Also, when you kind of sweep to go do the bit width calculation, you're going to get some pretty useful metadata that's going to fall out for free that you might want to actually stamp on the object, right? So, certainly you're going to get the range, right? And again, as you kind of do this consistently, what you start to find is, the performance wins stack up like a lot.
Yeah, I understand.
A lot.
So I just remembered now. So what I understand from you is that you're doing this aggressively. You're doing basically taking every data type that exists and
Yes.
trying to combine. So I know array languages traditionally do things like this, but they tend to restrict themselves to a few types rather than every possible type.
And anything worth doing is worth overdoing. So yeah, it happens.
There was a talk by Simon Garland that spoke about differences in the implementation of KQ and APL, and he said that there were APL traditionally has bit booleans, but that requires a lot of fancy bit flipping work to make all your algorithms work. But it does create a huge difference in performance because, I mean, at worst, an eighth of the data going across. I mean,
but then when you want to do something like, get the average over the Boolean array to give you like a probability, then you have to kind of start going the other way.
Well, you don't have to explode it up to bytes, because you could the processor has pop counts, right?
Yep.
So there are lots and lots of fancy tricks you can do, and the the processors have like APL functions like expand and compress and things like that, and that they can do. But I remember he spoke about, that's where I want to get to here. He spoke about the changes or the differences in how you design the language based on how it's implemented. And I thought that was really interesting, that because K doesn't have bit booleans, there's no point in having a primitive built-in verb, whatever you want to call it, of compress. Rather, you just use indexing with a where, right? So you convert the boolean to indices, and then at that point you lose a lot of the length, because all the zeros go away, and at least if it's shorter than 256, then it's not going to blow up the type for the indices being there. Every element, every boolean is 1 byte, so it doesn't make a difference. And so you don't need a compressed function. Therefore, K doesn't have a compressed function; it just uses indexing with where. Whereas APL, that does have bit booleans, does have compress, and it's a huge waste to blow up a boolean that's already pegged to integers before you do that. So now, here's the kicker then. If you aggressively pursue all these internal representations, such that I'm sure you do have bit booleans then, and isn't the language then like, doesn't it fight you in that way? The way people write the code forces you to blow up your beautiful bit booleans to ugly big integers.
And so you are describing essentially the 3-year nightmare of stepping back and saying, okay, all right, this works. What of these what of these verbs and adverbs do I need basically result in materializing. And then
Right.
you just sit there very quietly with a giant yellow notebook and you knock them all out. And you can't knock all of them out. So like some of the transcendentals, obviously you do just because of kind of the nature of that, you do need to materialize them. But then you start thinking about, well, do I need to materialize the whole array? Or do I only need to materialize, you know, so I can move the array into the cache line, but then when I'm doing the operation, I have to do a small materialization. I can, you know, maybe store that in a scratch offset. Can I still save some memory bandwidth moving over? So the ideal scenario is, you know, kind of a closed form of compute uncompressed. You want to get all of those that you can. And then, you know, worst case scenario, you want to get to kind of a partial form of compute uncompressed, where you're like, all right, well, at least I'm going to move this much smaller thing over the memory bandwidth, but then I am actually going to have to work kind of, you know, allocate a little space on the stack. I'm going to have to explode this thing up and do a little bit of work and take it chunk by chunk. But yeah, Adam, I actually have like a grid of all of the verbs, and I don't know if I have it in front of me, but I can send it to you where it's got all the verbs, and you can see kind of over time where it goes from basically red, where you had to materialize, to green, where it operates compute uncompressed.
So you're saying, okay, so you're also aggressively using things like arithmetic progression vectors for things like indices, so they stay small.
Yeah.
But do you also, I don't know if it's a universal term or something. There's something, at least in some area, some people use the term thunks, where the language does not actually evaluate some code, but rather remembers that this verb needs to be applied to this noun, but doesn't do it until necessary. So for example, you could do that. If somebody does a where on a Boolean in order to index, then you wouldn't do the where on the Boolean. You would remember that this where needs to be applied on this array. And then when you get to the indexing, then the interpreter goes, oh, wait a minute, indexing on something where needs to be applied on a Boolean. I know this, that's just a replicate. So then it goes in and directly takes the Booleans and does the filtering and skips the whole materialization of the indices.
Yeah, there's no kind of delayed compute there, or at least not in L.
Yet.
But it does have a concept of fusion.
Yeah.
So fusion, you know, fusion I think is a really loaded term. Rick Fasani works with this on me. So fusion means different things to different people. So for the easy case, it basically means no intermediates, right? So if I, you know, if I do whatever, some square root x, right? Can I do this without creating intermediates? Or better yet, would be like a chain of functions where it's, you know, array, where the output is array.
If you do 2 plus 3 times an array, right? So then since you need to loop over the array to do the 3 times, you might as well do 2 plus 3 on each one separately.
Yeah, and then then you just hate yourself. So.
But how do you do that without being lazy?
Yeah, so essentially underneath the covers, every array you can borrow. Basically, you can think about it almost like copy on write. So when an input comes in, it can be kind of borrowed, which means you can mutate it, or it's, you know, it's effectively you're operating on a copy. And then you can just mutate the intermediates, and then you don't really have those intermediates. You know what I'm saying? You're kind of working directly. You're literally mutating. The input comes in and it's like, hey, this is safe to mutate. You do square root on it, mutate it in place.
Right. You mean you have a ref count on the array, right? If the ref count is 1, you know you can do it in place with it.
Yep. And you kind of have to do that way up in the beginning. And then that's the other concept of fusion, is this idea of, hey, we're going to, if we detect, and there's this is done in L, like I think it's done pretty much everywhere else, which is just basically with kind of a table of known operators. But if you see this, kind of bytecode type, this structure of bytecode, let's go ahead and replace it with this other function, right? So, and L does that in its 𝗙𝗏𝗀𝗪 implementation. So it uses, actually, it looks very similar to 𝗦𝗛𝗢𝗪 from 𝗦𝗛𝗢𝗪. So it kind of looks at the bytecode and goes, aha, you're doing, you're doing where array greater than X. Okay, there's actually a different kernel for this that I'm just gonna like swap out that bytecode and replace it with this other one. That's gonna be a lot faster.
But again, if you do where array is greater than X, I mean, if you're just naively executing this code, then you see the comparison, you do the comparison, then you get to the where. Surely there must be some amount of laziness for it to even recognize the pattern.
There's no laziness. It will actually, Rick and I talk about working vertically versus horizontally. So you might want to, under certain operations, instead of doing the whole vector A, then the whole vector B, then the whole vector C, you actually might want to flip it on its side and do, operator, 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 operator.
Yeah, right. That's the fusion, really.
Yep. Yeah. And so we'll swap that out. That little bit we'll swap out.
So the interpreter reads ahead of what's coming. That's how it works.
Well, it just looks at the bytecode. So when you write the function, right, you write foo whatever. That gives you the bytecode.
Okay.
Yeah. And then when the thing goes to do the generating the bytecode, it's like, okay, I've made this bytecode just the way you asked. And then
I think I get it. Okay,
yeah.
So there's a.
It's not as complex as
No. I think I get it now. So it's
Yeah.
sort of like halfway compiled, right? Then the interpreter goes through, takes the code, converts it. I suppose it builds some AST internally for the function that these, and then it recognizes parts of the branches on the tree, and then it says, oh, I know this tree branch. Let's change that to something else. There you have an advantage we can't do in a dialog.
Yeah,
because we're not statically parsable.
That's actually how, I mean, unfortunately it does have to do it in a 2-pass, but it doesn't really matter. But yeah, that's how 𝗦𝗛𝗢𝗪 does kind of 𝗦𝗛𝗢𝗀𝗀𝗪 in a lot of ways, is kind of looking at the intermediate representation, and that's where the swap out happens. So and I think that's kind of the fun part. It's nice to have the restriction of this code must run this language standard, and you're like, but I want to do this, and it's like, all right, well then you have to do it without changing that code or changing that language, right? So 𝗙𝗏𝗀𝗪𝗀, which kind of does that walk over the interpreter, over the bytecode, or the actual object storage, where it's like, I'm giving you an array of dates, and it's like, okay, I'm going to tell you it's an array of dates, but I'm definitely not going to store it like that, and I'm not going to operate on it like that. And so I think these little things, they stack up. I've gotten reports in the field. I think the worst report I have from the field is that it's 6 times faster. And some of the best reports are just insane. But again, there's no magic trick here. It's just there are some places where you would probably want to change the language, although I'm nowhere near smart enough to write a better language. So instead, you just go, okay, well, I know that this combination of operators is more efficiently done this other way. And so I'm going to put that in my fusion table. And then if I see that bytecode, I'm just going to swap it out with this one.
So if I understand correct, this is super fascinating, and it was interesting too when you were listing off like the major 3 things. You left out the fusion, which I was like, wow, like if fusion doesn't even make the top 3, like that's pretty crazy.
Yeah.
So if
4. Okay, 4.
Or go ahead. Yeah, 4. If my understanding is correct, then so with the ref count, basically, reference counting, you avoid like the unnecessary allocations, which is like the biggest win. So does that mean that the 𝗦𝗛𝗢𝗪𝗔𝗔, not that that's what we're calling it, but you know, that kind of mechanism that's doing that fusion, if that doesn't have a pattern recognition for a certain thing, is it then like, so say in the example that Adam had where it was, you know, plus X, you know, times Y or whatever, if it didn't, I'm sure it does have recognizes that and then replaces the bytecode. But if it didn't, does that mean that you'll avoid the allocations, but you might end up iterating still the number of times the operations? So, but like, you basically, there's two pieces. You can expect to avoid allocations because of the reference counting, and then the bytecode pattern recognition, or whatever you want to call it. That's the one that like fuses the operation. So it's kind of like two pieces. You guarantee like your reference counting, if it's one, you'll get that piece, and then it's just a matter of it recognizing. I mean, it's very, and on top of, honestly, I had never, not to switch completely topics while I'm talking, I'd never heard of this, because Adam says, oh, you know, I think most languages, I had never heard of this kind of like separating or like compressing data into a smaller bit width by like basically storing a component of it, and then like, it's I don't know, it sounds novel to me because I've never thought about this, but then when you were like, oh, you know, if you just add a number, you can just do it to the base, and I was like, that's crazy. Like you turn what, even if you're going to use fusion, like, because that's typically the way I would solve that, right? Like there's an array language called cap that is implemented in Kotlin, and it's a lazy APL. So if you do a +1 or a +X, it'll defer, it won't do it. So you're not gonna pay like a linear time for that operation. It'll just bundle it with whatever it needs to down the road. But in your implementation, it's just an O1 operation. Like, who cares? And like that, then my brain is like, how many different cases like are there, like, you know, tricks like that where you can turn, you don't even need to fuse anything. Like you can turn what would be an ON operation into just like a constant time thing. And Adam, you said like this is classic. Like this is a lot of interpreters do this kind of thing. Like I'd never heard of this before.
In APL land, for commercial, like a real APL implementation, I think it's unheard of to not do type.
So this doesn't have a name like though. That's the thing. Like Jacob, you were saying that
we call it squeeze internally, but the APL never sees this, right? You can't. It's not directly observable unless the vendor put something into the language that lets you observe under the covers.
So
we have something
like we're
in dialog.
Episode 128, and I've never even heard of this concept. Like
I can show you. Dialog has something called 𝗦𝗢𝗪, data representation, and it will tell you what the internal representation is, how many bits per element, and what type it is. And you can see that if you give it one Boolean, it will say it's a byte. It doesn't bother to make it a bit because you're not going to save anything. If you then connect that, make a vector of 2 bits, then it will squeeze it down to a single byte. And it's just it has a length field, so it just says, okay, only the first 2 bits of this byte are actually the data that we're using. Right away, you cannot really stop it from doing that. I mean, you can tell the interpreter don't squeeze this array, but it's not going to stay forever. It will only be until it finds that it's convenient to do it anyway. And it's aggressive. It does it all the time. And even though there's so many checks for every operation, do another check. What can we now squeeze? It sure saves time. It would be unbearably slow if you didn't do this. And the bit Boolean algorithms are super optimized to do all kinds of crazy
tricks. Would you say, Jake, because it sounds like well, I mean, I guess you didn't come up with this idea. I mean, I'm hearing about it for the first time today, but apparently lots of folks know about this, you know, for decades. But like, you've taken this idea, pushed it to like, you know, 110%. And would you say, like, of the 4 different things, this is what gets you the largest percentage of the gain? Like, because you're saying you basically went back and rewrote, you know, most of the language, if not all of it, because of this.
That's really interesting too. That's the main thing, because I can tell you, in dialog has bit booleans, and then it has got 1, 2, and 4 byte integers, and then we've got 64-bit floats, and we have a crazy decimal 128-bit floats. We've got some 2 times 64-bit float complex numbers, and even for characters we do this. So even text data will be the 1, 2, or 4 byte per character. Or if you're writing ancient Chinese text, you're going to end up with 4 bytes per character. I know that APL Plus only has a single integer type. It does do bit booleans. I think every APL does. But then it just goes up to a full, I don't know if it uses 64-bit or 32-bit integer type, and then they have floats. And yeah, I didn't know that being so aggressive about the types would make such a big difference. I knew that it does make a difference to have this sort of thing, but certainly we don't do 2-bit integers and 4-bit integers.
Oh yeah, it makes all the difference in the world, because I think the thing that is different today than whatever 20 years ago, more than 20 years ago, when Arthur did K, is the CPUs are fast. It's the memory that's slow.
Yeah,
right?
that's well recognized.
Yeah, and it's I mean, the memory bandwidth is just fighting you everywhere along the path. And so, again, you got to just move less data.
So for all the mathematical verbs, are there libraries out there for like 4-bit integer multiplication, things like that? Because it's going to be a crazy mess.
Yeah, it's a mess. Yeah, it takes years.
Yeah, because either you blow up every time you do something, you blow up to, then you might as well not store it like that if you keep changing up and down. So you have to stay at your type and still do multiplications at every width and additions and etc. etc. That's some people described array languages and described for APL, but it would be the same across them all. That they're sort of like code libraries. You have some people, very clever people, working for many, many years to write all kinds of extreme algorithms for doing things well. And then you just use a simple symbol, a glyph, and you get all that hard work.
Yeah. And there are some libraries that do things like kind of fixed point arithmetic, and there's a GNU library that's kind of really good about but I mean, at the end of the day, that none of that stuff really helped. Papers help, but eventually you got to roll up your sleeves and just do the implementation. And the trick is, since you can't change the language, you have to think about making the codec standard, right? So even though there's a bunch of codec under the covers, they all effectively share this concept of like a base and a payload and then a patch. You don't need a patch for frame of reference, but yeah, you can. I will get you the HTML document, and you can see what's left. I think the only ones that are really left are the transcendentals. You have to do them partially, but you have to do them partially if you're not doing the fast math versions.
It also helps you that language has a small vocabulary and not so mathematics oriented. For APL, this would be a nightmare because of all the fancy built-ins, and for something like J, it would be
it's funny. I think I am not a language developer. I could never write a language. I do not have that much creativity and elegance and foresight, and I don't have any of that. I'm a mechanic. But the simpler the language, the more you can do with it, right? So, again, I've mentioned him a couple of times, but like 𝗦𝗛𝗢𝗪 is, I still think, one of the most underappreciated pieces of code. And the reason why you can get away with it is because Lua is so simple. Q is actually very messy, but K itself, Q is built in K, but K itself is actually very simple and super elegant, and it's not a giant surface. So if you can, if you start with something simpler, you can actually squeeze a lot of performance, and you can do a lot of these tricks because it's a nice, well-bounded framework that you're going to work inside. So, and yeah, you can, in L, it's not I mean, it's not hidden, you can do it, but you can do -17 bang. Negative int bang is kind of the KQ world of, I've got this function, but I don't know what to call it yet or something. And you can do -17 bang, and you can see kind of what is the object stored, and like how many bytes is the object compressed, which it should always be yes, and then how many bytes is it actually storing versus how many bytes was it originally. And you know, the other thing is, again, this is not a, like, K and Q and L, they are not show horses. They're workhorses. Like, they're not, they're due to that, you know, these languages are built to do very specific, very kind of distinct workloads. And, you know, database style workloads and financial style workloads. And so, you know, you don't have to, you have to be able to solve those problems. You don't have to be able to solve all problems. So, I mean, again, K always had a concept of a comparison tolerance. And that's like, you know, I don't know if that's how it works in APL, right? If you've got two 64-bit floats and they're almost the same, but not exactly the same, like at what point do you say those are equal?
Yes, APL has at least for a very long time has had a configurable comparison tolerance. That's what it's called, and as well. But I know J's is fixed. I don't think you can change it. I suppose K's is also fixed. And,
K's is fixed. L's is fixed. And
is it a multiplicative comparison tolerance? So it's like there has to be a factor of 1 plus 10 to the power of -17 maximum ratio between them, right?
Yep. So, which is almost a shame, because then you can't really do the then you can't just do the mem compare.
Exactly. Yeah, that makes float operations much slower, and it would be sort of nice to not do that. Right?
Unless you've got a compression codec that kind of knows that from the beginning, right? Sorry, Stephen has his hand up.
Yeah, I was going to say, hop in here. And also, too, we've got 2 questions in the chat. So we'll probably ask those in a little bit. But yeah, if you have questions, feel free to queue them up, and we'll make sure to get to go to those in a bit. But yeah, Stephen, go ahead.
Well, Jake, we've spent a little time exploring the implementation of how you manage to get ahead on performance. And I'd like to ask you a version of the question I was asking you the other day on our call. You've got an interpreter that has 100% coverage of the Q language and at least as much speed, to put it mildly. What do you want for this language? I'm not asking for a price. I want to know what you want to happen.
No, I think you need, we need more K and Q developers. We need a giant army of people building great systems, great code, and it needs to be out there. Like you know, recently I've been doing a lot of work with kind of AI folks, and you know, it's like, why did Python win data science? This is pretty easy because everyone can use Python, and there's a million packages. You know, SciPy is amazing. Like, I mean, it is actually amazing, but boy, is it slow, and boy, is it verbose. And I think, you know, I think there were really 2 problems here. One was, you know, unless you were kind of a member of the Illuminati, getting access to these interpreters was very difficult. And that obviously needed to go away. And then I think the second one was, you know, even though, you know, people like 𝗏𝗏 have done great work on documentation and books and implementations, there wasn't, even if you had the interpreter and you had some base knowledge like Q for Mortals or something, It's still difficult. You kind of learn this language, or at least I did. You know, this language was kind of passed down like a secret from one person to another. You would learn, you know, and I think that LLMs are making that go away. You know, you can ask whatever, sub your favorite LLM in, but you can ask your favorite LLM how to do something in an idiomatic way, and you tend to get right answers. And I think, you know, I think of the LLM as like an infinitely patient teacher, right? So now it's not perfect, but you know, as I always say to people when you have new technology, it's like, hey, just remember, this is the worst it's ever going to be. So, you know, and especially in the array languages, I don't know about you guys, but I have always said, it's like, I will go think about something for hours and hours. And then it might take me 5 minutes to code it. Like, the actual act of writing the code is never the hard part. Like, never. Like, the language is so simple. You learn to think in that structure. You know, you start to recognize patterns. And, you know, whereas like you look at today and it's like, you know, oh, people aren't thinking at all. And this LM is just vomiting out this, you know, truckload of Python that's going to slowly set the world on fire through its inefficiency. And it's like, hey, can we get back to like a craft? Like, we actually, some of us actually want to do this as an actual craft. Can we get back to thinking about, and then, you know, writing less code, reading less code, debugging less code? Like, can we get back to that world? I don't know. I mean, soup to nuts is, I mean, and it's a lot, but it's maybe 12,000 lines of C. And you got to keep in mind that every line of C can only be 80 characters because I am absolutely crazy. So you know, how do people debug a million lines of code? I have no idea. I mean, debugging more than 500 is just like, takes me all day. So I like small shortcuts. So can we get everybody an interpreter? I think there's a lot of great education documents out there, and people, you know, you should start playing with LLMs. Like, you can ask it to write idiomatic Q, and you know, it'll do an okay job. And again, today's the worst it's ever going to be. And so, you know, I'll give you a great example of this. Now that you have an interpreter and you can kind of run it anywhere you want, you can make that a tool call. So you can take this very, you know, kind of maybe an LLM that doesn't write great code, and you can let it call the interpreter and just iterate. And then, you know, you can fine tune it till it learns how this works. So, so yeah, I think those are kind of the main goals. And also, I think, you know, I think it's awesome that everybody, it seems like every single person right now is like, I'm going to go build a language. And like, man, do I honor that. But there's something to taking a language that has a big footprint. I mean, it has a bigger footprint than I think people realize. And just making it faster. Like, you don't actually have to go build a new language. Like, why would somebody continue to do work in K and Q? It's like, it's still got to be the bleeding edge of performance. I mean, it's amazing to me how fast K and Q is for the, you know, the style of workload that it does. And, you know, we're talking about effectively almost 20-year code. I mean, I'm sure there's lots of improvements that have happened, but fundamentally it's 20-year-old code. So can you get another order of magnitude? You know, and that's not just on the language side, but really, guys, the database is what makes this thing live, right? It's the database workload that people buy it for, use it for, implement it for. And And, can you be an order of magnitude faster than other things? And it turns out, yeah, you can, but you have to, make it small. And it's binary sizes matter. Like iCache matters. Like these things all matter. These are all parts of the craft that I think somewhere along the way got lost. Maybe everybody should, go back to having 256K dial-up to force a diet, like a GLP-1 for computer science. But yeah, that's kind of what my thoughts are there. So right now, can you make it faster than everything? It's pretty far on its way. Even on the database side, I don't know if you guys have ever used DuckDB. DuckDB is an amazing, great piece of code. And by the way, Adam, it has some of these compression codec concepts built into it, but for database workloads. I think Duck uses, for its loading point, I think it uses ALP, which is basically you take your, take whatever ill-gotten youth handed you money in decimals. This basically takes that and says, okay, well, we're going to write a compression codec that's going to effectively raise things to the power, raise things to different powers of 10 to see if we can get this guy up in the integer space. And then, of course,
that's really interesting.
Yeah.
That means you have to have some fuzz, right? Because a lot of things will be almost fit.
Yeah,
there's
a really good paper, the ALP paper, which is out of, I think, the CMI group. We could put it in the show notes. Kind of describes this, but I think I don't know about you, but like I am a small little things and then interlock them, right? So you could even take that concept, right? So say Timmy hands you an array of US dollar in floats, and you could just raise that to a power of 10, and everything would be okay. But then if you were to interlock that with the frame of reference, right, and remove that base off, and not take that payload, well, hey, those two codec interlock together actually give you like an insanely efficient way to work in the integer space on a smaller bit. You know what I'm saying? Like these things all get interlocked. I think people, would look at kind of, especially if you looked at like some of the stuff that Arthur did make open, it was like, oh my God, this interlocking mess. And it's like, no. Like that's exactly how you want to do it. Like if you have one function that's not interlocked with something else, you got to ask yourself, do I need that function? Or is there some other way to tie these guys together? I mean, there's literally on the L, kind of to build L takes a long time because it runs all these tests. And one of the tests is essentially going through and looking at the assembly, it gets output for every function. That can often be inline and other functions, but making sure that they all fit within the iCache, right? And if it isn't, then you got to go back and be like, all right, is there a way I can shave off, a few bytes off of this thing because I know that this is going to be interlocked into all these other places. So yeah, I don't know. I went on a little bit of a diatribe there, Stephen, but that's the goal, right? More people using this language, doing this craft, and like, please, for the love of God, stop handing me pages of code and then be like, can you find my bug? It's like my answer is always like, yes, I found your bug right away. It's this entire page of code. Give me 20. The RAG engine that I built with, for these friends. I mean, it's 20 lines. It's 20 lines, and it's way faster than what they were using, which was this giant commercial product. And it's like, okay, it's 20 lines. Like, we can all read it. Yes, there's some complexity here because they're dense 20 lines, but like we all can read and understand this. Like you can actually map it in your head versus the other thing, which was like, I don't even know, tens of thousands of lines I was like, dude, how will you ever find the bug here? Like, or by the way, finding a bug and optimizing it are just whether or not you admit it's broken or it, you know, you don't admit it's broken. Like if it's slow, it's still broken. So, you know.
It's interesting. You say this about the amount of code and the problem. A problem with LLM is that people are spitting out giant amounts of code. What I found, so I had, going back to what I said right in the beginning when before we introduced our guests, this game that I had made and that I've written it in JavaScript with one hand, because the other was on the baby, and so by necessity, but also because that's how I like to do it, I wrote it in a special, should we say, variant of JavaScript that I like to call 𝗏𝗏𝗏𝗧 JavaScript, where I don't know if Arthur has ever written any JavaScript, and I would ask him if I met him, but in what I imagine it would look like if you wrote it after having seen some of the code. Mind you, I don't understand C. I don't read C, but I've seen some of the things he's written, and I figured this is how we'd write it. So, 1-letter variables, 2-letter variables when necessary, and no unnecessary white space, keeping the code visible on the screen at any given time.
You can actually Google Arthur's JavaScript. There's one called 𝗏𝗏𝗏𝗏𝗏𝗏. Yeah, it's the connector. It was basically the IPC protocol parser in JavaScript.
C.S, you said?
C.js.
Oh, JS, yeah.
Yeah, I'll see if I can find it. But
okay, so this is how I like to write my Java in general. I also relied on every quirk available in the browser's JavaScript engine. That might not be the best idea to do that, but it makes my code shorter because I don't know. People have told me that you need to use things like const and let and var and I don't know what in JavaScript. I don't know what these words do. Apparently, my code does the same thing when I don't write it, so I don't write it. But my variables only survive very short before they more. So who cares if it's the global scope or whatever? So this is how I write it. And the interesting thing is that I was using Claude. I was able to get Claude to stick to this. So I did make it. I first got rid of all the quirks because apparently there are some features I needed JavaScript that are not available in quirks mode. But other than not writing super quirky code, so everything is sort of best standards, it still looks the same. Still makes actual JavaScript programmers go all white in the face when they see it and say, first reaction, that's not JavaScript. Second reaction is, oh wait, that is JavaScript, but what are you doing? You're not supposed to write code like that, and that's fine. But I was able to make Claude keep doing that, and that means that my whole game is like 250 lines of JavaScript, something like that.
Yeah. And I think it's
then I can actually go through it, even though it is 100 lines to 250 lines with Claude's additions, and more code than I can actually go through it and make sure that I know what everything is doing. No unnecessary bits, bytes.
I mean, everything's an abstraction anyway. Like you're not handwriting the stuff in assembler. So like the syntax, I don't think matters as much as people think it does, or the style doesn't matter as much as people think it does. It's, can you comprehend this? Like, what is the entropy? Like when you literally look at something, can you comprehend it faster? And by the way, like I'm sure that there are people for whom, basically reading a novel that kind of walks you through what's happening is better for them. But for me, I'll take a poem over a novel anytime. So,
Stephen, you got your
Yeah, Jake, for years, Q was my kind of go-to language when I had a license to use it for pretty much everything. And I would love to be one of the people you envisage for the future writing applications in Q or K. But for commercial applications, I will be writing them from a customer who's going to say, well, if anything goes wrong, who can I call who has to pick up the phone?
Yeah, I think you're asking kind of what is the long-term commercial plan for L, and I don't have one yet. So, you know, I think it's good to focus
right. It's
thing at a time.
it that make but using a brand name because that just
I don't know if it's just me, but I can barely make out what Adam is saying. Your audio has gotten
Yeah, it's
a little
breaking up.
choppy.
But yeah, I don't know what the long-term commercial application is. I think, you know, Stephen right now is, can you run all these workloads? And can you run them an order of magnitude faster? Let's try to get that first. And then, you know, then we'll deal with the next part next. Again, I think the good news is right, if you know, this is compatible, this is drop-in compatible. So, I mean, I think that works both ways. So you might have somebody who, you know, downloads L and builds something and then is like, you know, I could, you know, maybe if there wasn't an L commercial entity, then you can just be like, oh, well, you know, I have this code, I can call KX, and that's great. But because it is, you know, like I said, some of the reports from the field are pretty nuts, not just in terms of performance. And I hadn't actually contemplated this, but I feel stupid for not having contemplated it, is storage. So the, you know, the objects are compressed in memory on disk. I mean, it's all the same format. Again, do one thing and just do it everywhere. And somebody just basically moved over what is essentially a TAC database to see what the disk storage was. And it turns out like 8x less disk. Even then the dictionary compressed versions, which I think makes sense, right? Because, you know, dates and timestamps, the base type is a 32-bit and a 64-bit. They're almost always monotonic in the database, so they're always going to delta really well. And then they're going to frame of reference really well. And they're going to, you know, there's kind of one more trick that I do on the patch. And so you actually do end up like, yeah, like a column of time is going to be super, super small. If it's a high fidelity, like high frequency set of time, deltas are going to be tiny. And that's going to compress down a lot, like a lot. Dictionary compression just really isn't good for numbers. I don't know why people love dictionary compression. I mean, it's good for text, but it's not good for numbers. Yeah. Sorry, Adam. I don't know if your audio worked now. I wanted to answer your question, but I couldn't quite make it out.
I'm sorry. I hope it's better now.
Okay.
Okay. I just need to reload. But let's see if I remember what it was.
It was in the middle
right.
of
No,
talking
I think
about
it's
the commercial plan.
Commercial plan, because it's sort of a joke, but there are these companies that sell knockoff products that branded like real big brands out there, and they, for customer support, they just list the originals contact information because their products are so identical to the real expensive thing that the customer support for the real deal is the same as for the cheap stuff that they're selling. It's sort of a joke, of course, because it's not commercially viable in the long run to say, you know, who do you call for assistance if something's not right? I know that your language behaves identically to KX product, then ask them or look at their documentation and so on. But that of course, that's a joke. That doesn't work. But But essentially, that's the situation you're in right now, right?
Well, and I think Stephen's point's a good point, right? Even open source code, you know, you're not going to take a piece of open source code, I mean, I guess except for the case of the operating system, and you know, go deploy that in a mission critical environment without somebody to call, which is why these kind of open source business models I think succeed. But yeah, again, just step one, get it compatible, which we're past that point. Get it fast. It's pretty fast. So, you know, I'm sure that we're going to discover more things that we can make faster. I'll give you a great example. So, K, and I don't know if APL has this concept, but K has a concept of a symbol, which is essentially a character string that gets mapped to essentially an enumeration, right? So if you have, this comes from its use case, right? So in Wall Street, you know, stocks have tickers, you know, like IBM and whatever. You obviously, you know, don't want to store a bunch of strings in a table. Like, no, again, terrible life choice. Don't do that. So what you want to do is you want to store those as a number, and then you've got a lookup that needs to happen, kind of an enumeration between this array of characters and its numeric representation that sits in the database. And that's great. And that works wonderful. Except you need to have that enumeration stored somewhere. Like if you lose that enumeration, and in K it's called the sim file, and if you lose that sim file, like you're smoked. Like you've just lost the map. Like the Torah is now gone. We have no idea how things work anymore. And this is both a kind of an operational problem, but it is also actually a performance problem. So in a scenario in which you want to run kind of parallel reads, you know, across multiple partitions, that symbol file needs to effectively be shared, right? All those partitions need to be able to decode that symbol file. And so you've got to have a lock on that symbol file. And, you know, to be completely honest, I didn't do any character codec because, you know, I don't use strings a lot. And the community was like, hey, this is great, but is there any way, basically they're asking, is there any way you can get rid of the sim file? And it's like, okay, what we're talking about is we just need a new codec here that will fit this. So again, be practical. It's a workhorse, not a shore horse, right? So most financial workloads, the character string is fairly short. So it's, you know, generally 4 or less characters, but certainly 8 or less characters most times. Those are holding the ticker, kind of the name of the stock, right? Well, you can, I don't know if you guys are familiar with this concept of German strings, but you can just basically take that character array, turn it into the numeric equivalent. And that has 2 benefits. One, it's a number. So, you know, God likes storing numbers. And 2, it's like lexicographically sortable, right? So sorting that number is the same as sorting the characters. So that was the first one. I did that, and it was like, hey, now you have no sim file. Every symbol vector is kind of self-describing, subject to you only using small character strings. And then, and if you use a large character string, then underneath the covers, that codec is going to have to switch to an enumeration, and like you're going to, you know, now you're back in pain. And then somebody in the community was like, yeah, but like these options ones, they're just a little bit longer. And I was like, well, then, you know, tell them to make them shorter. And it was like, well, no, you can't do that. So that was like the last, I don't know, 2-3 weeks was thinking of kind of what is a codec for storing a string that still allows you to have those properties. And so actually for a symbol, there is no enumeration anymore. They are all self-described. And each vector is kind of self-composed. And it's like, okay, that's great from an operational standpoint. You don't have to worry about losing a sim file and losing all your data. But boy, does that turn out to be a massive performance improvement, like massive, like more than an order of magnitude. Because all of these locks on the sim file go away. And because then if you have multiple sims in a table, you can now operate them on them independently. And of course, because all the codecs are sortable, you don't have to worry about this. You used to like have to go work on you would go into the enumeration, find the symbols that matter, then go back into the table and then find the match, and then no. So all of that just goes away. Yeah.
The sim file bloating is going away as well because there's
Yeah.
no more sim file.
Yeah.
Like one problem with the sim file is like it makes your data on disk faster, but as soon as you start bloat the sim file, you're losing this performance. And I've been teaching KDB developers and juniors, and often one of the grads, one of their rookie mistakes is like, okay, I'm making a column that's not supposed to be a symbolic column, a sim, and then you store it to disk and you blow up the size of the sim file, and now suddenly your HTTP isn't fast anymore. And then you have to deal with basically recreating your data, because there is no easy way to remove something that went into the sim file. You have to de-enumerate everything, re-enumerate it, and save it back down to disk. And that's like a massive pain and a very risky operation. So not having to deal with sim files, that's a pretty cool thing.
Yeah, and again, it's a massive performance unlock, because now you can have each one of these kind of parallel readers operate independently, and you don't have to worry about a lock. God has a couple of designing principles. He doesn't like characters, and he doesn't like locks, and he doesn't like branches. And the more you can get rid of those, the better life is. So, yeah.
Have you noticed other things, Alex, when using L versus your experience in the past?
I found it really easy to transition. It's pretty much like I came across this 2-3 weeks ago, and then Jake gave me the binary, installed it, run it, and I thought like I have to learn something new, or at least read some documentation. But Jake was basically, it's pretty much like Q, just start playing around with it, which I did, and I haven't seen much that I couldn't do. It's pretty good from what I've seen so far, and yeah, I like it.
Do you have any workflows that you notice got way faster, or do you not really have that kind of thing where you're running something regularly enough to notice?
No, I haven't. For now I've just done basic stuff. I didn't went too crazy on it yet. But yeah, I know Jacob ran some stats, and they look pretty promising. And one of my questions for Jacob was actually like, we've talked a lot about what you've already done in terms of to squeeze some performance out of it. Do you think you can push it even harder? Like, are you there yet with L? Are you finished? Do you think it's okay, that's the maximum we can squeeze out of it, or do you have a few more tricks in your sleeve?
Oh no, there's definitely more to do. There's always going to be more to do. I think I'm out of ideas for now, so that's why it's like you want more people to have this, because you want to, I'm out of ideas. So let's see if anybody else has got some new ideas. But I think I actually think the fusion 𝗢𝗢𝗪, where it actually goes and changes the bytecode. One of the things I want to do, and I just haven't figured out how to, is expose that up so that a developer can essentially write new fusion rules in the interpreter and save them down. Because that's that's where there's just a lot of institutional knowledge that it gives you just huge performance wins. Like, I mean, the classic example is, like Connor said, the fuse multiply add, right? Let's take this set of operators and let's just move it into a dot. But, you know, there's a lot more of them, like working with matrices and, you know, working with them in arrays and indexing into the matrix in kind of a straight linear fashion rather than a matrix. I don't know, as I come into more workloads, I'm sure there'll be more opportunities to make things better. But yeah, I'm kind of out of ideas of how to make it faster. So, and really it's like where if anywhere is it slow, right? So if it's, so for example, I didn't do like the string operations, like, you know, again, strings, I just don't use them. So, and then somebody in the community came in and they were like, man, this string search and replace is really slow. I was like, oh, okay, let's go back and fix that. So, went and fixed that. And, you know, stuff like that.
Speaking of this is a good time to ask one of the two questions, or maybe both, but one of them was relevant to the patterns that you mentioned. So the question is, all of those fusion patterns and compressed representations must lead to lots of combinations. Do you have special code for even, and I think it's e.g., for example, arithmetic progression vector plus a number plus frame of reference vector?
Oh, that's a good question. No, because all the verbs have the compression operations built in. It really is just purely on the function itself. You actually don't, there isn't actually any way to, in a fused operator, to say, do this if that is compressed with this codec, do this if it's compressed with that codec. But again, you don't really have to worry about that, because as long as you get all the verbs and adverbs working compute on compressed and closed form, that's really just an implementation detail. Where fusion really matters is, again, kind of institutional knowledge. I see this, it's better to do that. And that really is just like, you know, institutional knowledge, or tricks.
All right, so we'll go to the second question too, and then we'll go to Steven. So the first question was from Asher. I forgot to mention Asher's, I believe, a dialogue employee. So both of these are APLers. The second one's from Max. Is scan, this is rather specific, is scan linear or quadratic in L? Because across languages, sometimes it's quadratic.
It has to follow what K does, right?
Is scan linear or quadratic?
What he means to say is when you've got a verb followed by backslash, and you're taking the partial sums, whatever, to running some. Do you start over every time going from the left, or do you reuse the previous result? Because the point is that A verb B verb C by APL and NK grammar, you need to start to compute from the right to left. And therefore, there's also the idea that if you do a reduction, fold, insert, whatever you want to call it, then that's equivalent to just having all the elements spread out with a verb between them. So you need to go from right to left. Okay, that's all fine. Although we spoke about not worrying about commutativity of mathematical functions. But when you get the scan and you get a cumulative sum, then you cannot do a single pass computation, because you really need to go to the last element of the running sum has to be the last element plus the second to last element plus the third last element, and so on. But the second to last element, you have to start with the second to last element and go to the left. And if you're strict about this, if you're strict about the order of operations and strict that each partial sum must match the equivalent sum of that, and you're strict that the sum has to run in a element to element, so no SIMD, then you end up with a terrible performance because you have to start over for every element in the scan.
Right. Okay. So this is going to be a long answer. So but this is a place where Fusion plays. So,
but hold on, before you answer that, I think I can sort of sidestep the question. There are two things plays in. If I remember right, K's definition of a scan is strictly left to right. You just keep adding one more element. Right? That's the first thing. So the question doesn't come in. Second thing that sidestep the question is you don't care about the order of application of commutative functions. So this whole thing is only comes into that because of being strict about it. It would seem to me that there's nothing even to answer here.
Yeah,
obviously not.
There's nothing really, I think, beautiful or magical about this, but I will say this, that the fuse there in fuse.c, they're obviously operators. So prefix sums is something you use all the time, right? So that actually calls very specific C code for that problem. That allows not only to use SIM, and actually there's a great write-up on that on parallel prefix sums on Algorithmica, I think. But that one specifically, the sums, prods, mins, maxes, those all have custom C implementations because they are used specifically in their SIMD implemented and parallel implemented, and they're fairly bespoke. But if you were to do like F, create a function F and do like F scan, that will just operate like K, where it just goes, just kind of runs through it as fast as it can from left to right.
All right, you've waited patiently, Stephen. Now over to you.
Yeah, I want to comment a bit on the implications of what we've been hearing over the last hour. Romantic Alex Unterreiner and Romantic Stephen Taylor called a meeting to work on shared community Q libraries, and cold-eyed KDB devs said there's no use case for those and we're not coming. So we wound up canceling the meeting. And feeling very sad and having a little weep. And then Jake released his L interpreter. And now, I can't remember who I heard use this term first, but the language has got jailbroken. The first time we've got Q that you can use in a commercially performant interpreter and can use it anywhere, or at any rate, the prospect of it. And this seems to be the time for this, because there are other projects working on the same thing. Jake's the first to come forward with 100% coverage of the language. I think PeachQ is reporting 43% coverage, peachq.org. And John Estrada, with his 𝗏𝗧𝗘 interpreter, reckons he's at about 80%. So this is a completely new landscape for the language. It's broken out, it's jailbroken, and there's clearly a need for some kind of community meeting to work out what community resources could be shared between them and so forth, or what we need to do. And that will take some time to plan and organize. Meanwhile, at Milden Hall in September, there's the original failed meeting is coming back to life in some form, and neither Alex nor I quite knows what's happening there. But John Estrada will be there with 𝗏𝗧𝗘. His collaborator Rob Hodgkinson will be there from Australia. We're expecting Fintan from the States with Shakti. And we hear Dave Thomas is coming over to talk about what needs to be done for the community. So we don't even have an agenda for this, and we don't yet know who's coming or who needs to be there. But our celebrated chef is back. And so I'm basically putting this out there that if you listening are someone who wants to be in on the very the very ground zero of what looks like a first actual community for K and Q, get in touch with Alex or with me.
Yeah, and I gotta say, man, as someone who grew up in this community, you know, when I came to New York, I didn't know anybody. I got this job in New York at this, you know, at this shop, this 𝗓𝗏𝗪, and I literally reached out to the K community and was like, I'm here. Is anybody else here? And like the first beer I had, the first dinner I had, you know, the first apartment I went over to, you know, the first group of friends that I ever made was, you know, K and Q programmers. And like, you know, it's a quirky community, and I've been gone for a long time, so it's nice to come back and be reminded, like, oh, there's a whole city under here. Like this Discord server was like 4 people, and then it was like 40 people in like a weekend. Like, and yeah, I think there's, you know, I used to make jokes when I was people like, what is your preferred language? And I'm like, oh, I always prefer programming in K. And they're like, what is K? And I'm like, there's dozens of us. Like dozens. But that's not true. Like there's actually hundreds of us, and you know, maybe thousands of us soon. We just need to make sure people have access to it, can play with it, and like not play with it in just educational ways. Like the only way you actually, I say this all the time, the only way I can actually learn something is to use it in anger. Like it needs to be put in these situations where you have to make it work because something depends on it. Using things in anger is how you get good at things. So yeah, man, go download L and like go use her in anger. And if something's wrong or slow, or you know, just send a note. Well, like I'll take a look at it. We'll get it fixed. Like symbol file took 2 weeks. So, and you know, how hard could the rest of it be? So
the download's available obviously at the 𝗦𝗛𝗊𝗆 link. What's the best way if you run into issues or you just want to leave feedback? You mentioned a Discord, but that sounds like a smaller private thing. Is there a go-to space, GitHub issues or Twitter or something? What's the best way?
There's actually, when you go to that website, when you go to 𝗦𝗛𝗊𝗆, there's a mailing list, and you can join the mailing list, which is how it used to work in the olden days. I like the mailing. I mean, the Discord's fun, but I like the mailing list because it allows, you know, you can work a little more asynchronously. And Randy just, I think last night, got a forum up so that you can go and, you know, search old, see kind of the mailing list archives and be able to search it. So if you want to get in touch with me, that's certainly the best way. Just send, you know, join the mailing list and then send a message to the group, and then I'll get it.
One thing I want to add, and that comes from, you know, the early days when I started to learn Q. The original mailing list, everyone could see who sent an email to the mailing list. Now it was, you know, full with some veterans who have been doing Q for a long time, and it always felt intimidating to ask a question out in the wild, and then, you know, the imposter syndrome, wondering whether everyone is going to laugh about you and think you're stupid. So Jake actually made the mailing list anonymous. So whenever you send email to it, unless you have a signature in your Gmail address like I do, no one will actually see who sent it. So that's a good way to ask your question without worrying whether you're going to be exposed for asking something stupid, even though there are no stupid questions, only the ones not asked. And then for all the listeners who are not coming from a Q background or haven't learned the syntax yet, go check out my blog. DefconQ.tech, where you can actually learn the language and the syntax. And I think I did a pretty good job in explaining it in a very easy, comprehensible way. If anyone wants to chip in, Jacob, Stephen, you can give your opinion about it.
Yeah, I just downloaded it, and it runs. I was about to ask, wait, what if I'm on Windows? So
Not
You
yet,
should
that's
think
it.
about your life choices, Adam. That's you've made some bad turns in life if you've ended up.
well, Windows now has such a thing called as WSL that can run Linux things. So that's what I'm doing, and it works just
Does that
fine.
work?
Yeah, it works fine.
There you go. New platform supported.
Yeah,
Thank
so
you.
so that's fine. Now you know. But one thing you might want to do is make it available to run in the browser. I don't know if you can target WebAssembly or something like that with a C to WebAssembly thing or some.
I don't think that does WebAssembly have SIMD built in? It is deeply SIMD specific. So
I know there are things out there that are able to compile C code. I don't know what happens if it has deep SIMD things. I would imagine that it would work, but I don't know. I don't know anything about these things. But it would be something that's very nice for a language like with a sort of small existing audience is to have something you can try right away in your browser. So by whatever means necessary, like even if you need to run some kind of virtual machine thing that's in the browser that can then run it, that makes it very slow, but just that people can get a feel for it, that might be a nice thing. But then I found an interesting quirk of the L language. We can call it an inconsistency, but it sort of has to be the way it is. It's just funny, I think. I wanted to mention this. That is, I happen to know, I don't really know K or Q, but I happen to know that in Q, if you apply a string, a character vector, to the character K, then it gets evaluated as K code. So here's the fun thing. If the language name is L, this still works. It is implemented. I just tried it.
Yeah.
But that means the language sort of claims to to evaluate K code. I guess it does.
It does evaluate K code.
Yes, it does.
You can just hit the backslash and you actually drop into the K.
Yeah, that's the first thing I do.
Yeah.
I don't need no Q.
There you go.
Give me K.
Yeah,
So.
Q is complicated. K is a lot simpler. The only thing that is still gated, which I'll ungate soon, is the offload, the GPU offload. Again, it's just transparent. So I'll ungate that on the Mac first because the hardware is consistent and it has unified memory. But yeah, that's GPU go burr is really good for it's really good for sort at stupid large amounts. Actually, I mean, you have to have really, really, really big arrays for that thing to actually start to kick in. But when it does, it's pretty amazing.
We've got a comment in the chat from Madeline, who's mentioning that WASM has had SIMD for a while. So, I mean,
all right,
there's your answer. It could be possible.
There's maybe there's a project there. Maybe I'm not. I don't really do web development, but Randy LeBeau, who built like the forum and the anonymous email list and all that stuff, I'll ask him. If anybody could do it, he could do it. So see what we can do.
Max Meme God says that ArrayBox, please.
Well,
so
I mean,
once it runs in WASM, then you should be able to run it on the ArrayBox as well.
Once someone implements the WASM, it should be pretty straightforward. But one last thing too, because I know, Stephen, you mentioned for people to get in touch. Is there a website? What's the best way if people are interested in attending the upcoming event? Is it to reach out to you? Is there another mailing list? Just so that I'm sure of the folks that are listening, there's going to be a handful of folks that are interested. So I want to make sure I'm pointing them in the right direction.
As we record this, it's not there, but on iversoncollege.com, there'll be a notice about what's happening with the meeting, or at any rate, what we know about it, and an invitation to reach out to anyone who thinks that they'd like to be at the potential ground zero of a new, or what should we call ourselves, Alex? Communards?
I like that.
All right. So, I mean, if you're listening now, you can check iversoncollege.com. If it's not there yet, Stephen will let us know, Adam and myself. And when it is live, probably by the next time we're releasing one of these ArrayCasts, we'll be sure to announce it and point people in that direction. And with that, I will say thank you so much to all of Jacob, Alex, and Stephen. This has been awesome. I've learned a ton. I mean, it's super exciting. I didn't realize that it's not just L out there. I learned about 𝗏𝗀, and you mentioned a couple other ones. We'll be sure to link all of the different flavors of these, I guess, Q implementations that are out there. And will be very exciting if you are having a meeting and folks are getting together. Because, yeah, it kind of feels like I don't know, maybe Renaissance is a bit generous, but it feels like there's a shift in the Q wins, and the same way that there's, a number of APL implementations, whether they're hobby projects or more serious. But yeah, this is, as an enthusiast of different array languages, it's very exciting to see this kind of development happening. So, yeah, thank you so much for coming on, and we'll be sure to link to all the different things that we mentioned in both the YouTube description and the show notes, so check those. And with that, we will say, happy array programming.
Uh,